Welcome back. So for those who don't know you, my name is David Poulet. I'm one of the scientific organizers of this meeting, and I'm just here to introduce the speaker this morning, Verstraete, who will be telling us about the Tensor network. There you go.
Thanks. It's a great pleasure to be here and to talk about tensor networks, but of course tensor networks are seen in a much more broad way from the point of view of quantum many-body physics or entanglement theory. So I guess most of your interests lie in quantum information theory and quantum computing. But this is but one of the most genuine real manifestations of quantum information that has already kind of come to the surface really because of this whole field of quantum computing that gives you a new language for describing quantum correlations is a novel way of dealing with the quantum many-body problem. Okay, so the quantum information theory, in some sense, has already had some impact in real physics because it really provides a new language for looking at problems that have been around for a very, very long time. Okay, so if you look at all the big problems in theoretical quantum physics or chemistry in the last or since 1925, basically, that was the moment that Dirac already immediately wrote down these famous words in which he said that indeed, well, we know the equations of quantum mechanics, but that doesn't mean that we know how to use them, how to solve the equations, because the equations become extremely complicated if you have many particles. And people were aware of this from the very beginning of quantum mechanics, and since then all the big, or from my point of view at least, all the big breakthroughs in theoretical physics, but also in chemistry, have been ways of dealing with, somehow, to find approximate ways of dealing with this quantum many-body problem. How do you deal with these Schrödinger equations when the number of particles or the number of variables or the number of degrees of freedom scales linearly with the system size? It means that the Hilbert space dimension scales exponentially at best, but typically it's always infinite dimensional. So quantum mechanics is really, since then, became a way of trying to get a handle on these Schrödinger equations, and specifically to find approximate ways of solving them. And what I would like to convey in this first lecture is to give you some feeling of why this is. What are these kind of things, or what fields? Or I would like to give some introduction to such that you have a feeling of why entanglement theory and the theory that is developed basically to describe quantum computing can be useful in giving new insights into this central problem in quantum physics. So please interrupt me anytime and ask questions. The more questions I get, the better. So if you look at theoretical physics, condensed matter physics, statistical physics, quantum chemistry, quantum field theory, hi, Graham, it's all about strong quantum. So the big challenging open questions are all about quantum correlations. How do you deal with the quantum many-body problem? How do you deal with the strong correlations, the quantum correlations in the systems? And of course, you have already had many lectures now on entanglement theory, and you know, well, correlations, quantum correlations, entanglement, it's all the same. So there's no, so it's just a big, it's just one word for dealing with somehow this. It's all a consequence of the superposition principle of quantum mechanics. So what are the problems that people, for example, in chemistry want to deal with? So a huge leap in the field of quantum chemistry, and by the way, this is, you probably had already lectures on this, how to solve quantum chemistry, or how to at least get some new insights in quantum chemistry using quantum computers. This is of course exactly the same problem that we are trying to tackle here, and we are trying to understand exactly the same quantum correlations. So it turns out that both this quantum computing, this field of quantum computing, both gives you potential way of solving these problems with quantum computing, but also it might give you really kind of new insights or new kind of might lead to new developments or new methods for trying to solve these equations using the theory of entanglement and specifically in terms of tensor networks. But anyway, what is quantum chemistry about? So it's think about a molecule, and the first thing you have to do is to make some abstraction of this molecule. So you have this big molecule with all the degrees of freedom, and you want to reduce the Hilbert space dimension. Of course, these molecules, these electrons, they live in an infinite dimensional Hilbert space. But then what you do is some things like Hartree-Fock. You try to find some Gaussian approximation for the lowest energy or the relevant degrees of freedom in the system, and this reduces this problem from an infinite dimensional problem, namely when you have like all the Schrödinger equation with your continuous variables, to just some modes. Okay, so so where should I start actually my lecture? Should I start here? Or should I only use the middle board? What did the other lecturers do? All of them are fine. You guys are very sharp. You are very sharp. So this quantum chemistry problem is, so in some sense what you start doing is reduce this infinite dimensional problem to a problem of local modes. Okay, so you say I have like for the hydrogen atom, so I would like to describe a molecule where there's some hydrogen inside it. Well, you kind of look at the hydrogen and you say, okay, let me kind of take the 1s, the 2s, I forgot the names of all the other orbitals, d, p, all these kind of things, and this gives you a way of going from this infinite dimensional Hilbert space to a finite number of degrees of freedom, and at the end what you end up is some Hamiltonian that can be written as some ijkl, let's call it hijkl, psi I dagger, psi j dagger, psi k, psi l, with these field operators or kind of basically these label nothing more than the basis states. So I guess most of you are familiar with the theory of second quantization, or is that not true? Is everybody familiar with second quantization? Yes? Yes, good. Okay, so but I guess this has been covered in previous lectures, because certainly people in quantum computing are not always familiar with this notation. But anyway, this is nothing more than the basis states where you kind of have some particle preservation. But at the end, what you have is a local Hamiltonian, localized in the fact that the only terms that act on your that you only have like 4 body terms here. Okay, so you have only you never have terms that act on more than 4 modes together. But anyway, so you are trying to find the ground. So how did you find these modes? Is by first doing some Hartree-Fock calculation. Okay, so this Hartree-Fock calculation is a very approximate way of finding the modes in which you want to represent your problem, and then you still have to, of course, solve the whole problem within this reduced Hilbert space. Okay, and so the problem that is that this Hartree-Fock solution typically is not sensitive enough to give you enough precision, enough chemical precision. Okay, so you need to have better chemical precision, and you cannot get this with these Hartree-Fock wave functions, which are in some sense mean field variational wave functions. And you would like to really go beyond that, and that's exactly the question that people in quantum chemistry, this is the central question in quantum chemistry, is how do you find basically ground states of this model? So you would think, why is it only so certainly when I was kind of new in this field of quantum ManyBody physics, I always wondered why people are so much interested in ground states, because at the end nature is we always have some finite temperature and so further. Why is the ground state so important? Well, we'll come back to this later in this lecture, but it turns out that indeed for quantum ManyBody systems, once you have the ground state, you basically also have access to all the other low-lying excited states. So the locality, and this is an extremely surprising thing, so once you find the ground state of a Hamiltonian with some notion of locality, then this automatically also encodes information about all the low-lying eigenstates, not just the ground state. So this is something that is completely absurd from the point of view of linear algebra. If I give you a matrix and I give you one eigenvector of this matrix, well, the other eigenvectors of this Hermitian matrix, the only thing you know is that they are orthogonal to it, but you don't have much information. Well, the physics is different. Physics has some extra labels, has some extra information, namely that this Hamiltonian is a sum of local terms. And all the physics, the fact that we can do physics at all is actually a consequence of this locality. Okay, so otherwise it would be completely impossible to do physics. So it's the locality of your Hamiltonian or of your interactions that allows you to actually do physics at all. And that's as a consequence, if you find the ground state, it turns out that indeed these other kind of states that you will have if you have some kind of finite temperature, you will excite somehow low-lying excited states, because actually for electronic systems, typically the even finite temperature, even room temperature is actually very small if you compare this to the energies involved with relation to your Fermi kind of energy. Like if you have a system of electrons that on a lattice, like a Hubbard type of model. Well, somehow if you would really kind of look at a real material, the typical energy scales that electrons have is like 10,000 Kelvin if you would express it in terms of temperature. And that means that room temperature, even room temperature for electronic systems, is very, very low temperature. That's why once you have the ground state, you kind of get lots of information. And as we will see later, once you find the ground state, you can get over that. Okay, so this is like the typical. So in some sense, this is the generic problem. Both chemistry, condensed matter, high energy physics, in some sense, can be treated in many ways, starting from such a very generic Hamiltonian. But chemistry is typically very dirty, because somehow there's not much symmetries in these Hamiltonian terms. So to make lots of progress, like in physics, you would like to kind of reduce the number or the amount or the possible types of interactions, and that's exactly what people do in condensed matter. So if you have like a system with some extra symmetry, namely you have some crystal, some underlying translation invariant in your theory, or somehow these interactions turn out to be very not long range at all, but very, very localized, such that only the modes, that if you associate these modes to the local degrees of freedom, that only these modes that are kind of next to each other or very close to each other interact with each other, then you will be able to make lots of progress and go get lots of mileage out of it. And this is exactly what you want to do. So where are these quantum correlations important? Because it doesn't matter if you kind of have some Hubbard type of model. I suppose that you have already seen this in the previous lectures. You could say, well, let's do the same thing. Let's try to first approximate the ground state of the system using some Hartree-Fock wave function, some Gaussian ansatz, and then see how far we get above that. Well, it turns out that you for many systems out of interest, this works extremely well, but for the systems that are really exotic, have exotic quantum correlations, or somehow really the properties that or the systems actually that we don't understand, and at the end we are all researchers, so we are only interested in things that we don't understand. Then you really need to kind of take into account these quantum correlations. And so you probably heard about this very recent discovery of twisted graphene, when you have like two graphene layers and you put them on top of each other and they are twisted by some angle. I'm not so sure anymore. It's like 1 degree or 1.1 degrees. And it turns out that it has very exotic properties. It has some very interesting features related to superconductivity. Well, it turns out that the reason that people don't understand this yet is exactly because the interactions are important. Okay, so this is there's many materials. Also, high TC superconductivity. This has been the big open problem in condensed matter physics, in which actually not much theoretical progress has been made in many years. And also there, it turns out that the reason that not much progress has been made seems to be that we don't understand the correlation, the quantum correlations, the things that go beyond this Hartree-Fock mean field theory. So it's very, very difficult to deal with this. So actually, so we covered chemistry, condensed matter. So in order of increased symmetry, you also have like statistical physics. So one of the things that is actually kind of strange and goes a little bit against this whole paradigm that quantum is so great and everything, if you put quantum in it, everything becomes so much richer and interesting. So if you look at quantum many-body physics or just classical many-body physics, turns out that there's not that many new kind of phenomena that happen in the quantum regime as opposed to the classical regime. So if you have phase transitions and very exotic kind of anions and all these things, well, there's for most of these things that we intuitively believe that are really quantum phenomena, there turns out that there's many classical systems that exhibit very similar features. And of course this has been a field in statistical physics that has been developed forever, and many of the features that arise, or many of the difficulties that you have in the quantum problem, also are there in the classical statistical mechanics problem, because it's the same. So in many ways, the statistical mechanics or classical stat mech let's say in d dimensions is very similar to quantum dimension in d-1 dimension. So this is certainly something that you have heard already in your physics lectures, and indeed it is for many problems possible to reduce a quantum problem to a classical problem by adding this dimension, by looking at a quantum Monte Carlo kind of a path integral, by looking at it from the point of view of path integral. So a path integral does nothing more than map basically a quantum system to a classical system in one dimension larger, and that's why one dimension higher, and that's why it's not so surprising that indeed many of the interesting phenomena that happen in the quantum regime are actually already there also in the classical stat mech sense. And so this, of course, the model that most of you have certainly seen and understand very well, or the Ising, or for example, the Ising model in 2D, the classical stat mech Ising model in 2D. Well, indeed, this is completely in one-to-one correspondence with the quantum Ising model in 1+1D, so in one dimension, basically. So if people in the quantum, in quantum, especially people in quantum field theory say 1+1 dimension, this just means one spatial dimension and one kind of temporal dimension, because you also have time, and stat mech is typically in equilibrium, so it's like 2+0, and 1+1 is indeed 2+0. That's the kind of reasoning. But anyway, so there's lots of interesting phenomena that happen in statistical mechanics, and indeed the way, if you kind of look at people, how people in condensed matter, in the field of condensed matter, deal with the quantum many-body problem, many times they use the intuition of the classical stat mech to describe basically what is going on in the quantum regime. So I'm thinking about things like in the classical systems, in classical stat mech, things like the XY model or Luttinger liquids and all this. These are things that both appear in the quantum and the classical regime, and indeed the physics of these two things is exactly the same. And actually this is I think there's an interesting problem to if you're sitting on somehow in a conference on a table, and you don't really know what to say to your neighbors who are all kind of physicists. I think this is always a very fruitful kind of discussion theme, to ask whether there's actually anything quantum that has no classical counterpart for quantum many-body physics. And at first you would say, of course, there's many things that I can think about, but it's actually very hard to come up with things in the context of quantum many-body physics that is purely quantum and doesn't have a classical counterpart. Okay, so then another kind of added symmetry is now to go to high energy physics, to quantum field theory. So what is going on? So what do people do in quantum field theory? So quantum field theory is in some sense some making abstraction of the UV degrees of freedom of your very small range degrees of freedom. So the microscopic degrees of freedom are in many ways irrelevant if you have a quantum many-body system for the long-range properties. And so the whole mantra of people in quantum field theory is that indeed, if I know basically my condensed matter system, or I know my Hamiltonian of my quantum many-body system, and it has a certain number of symmetries, then I will kind of be able to make abstraction and write down quantum field theory directly in the continuum with the same symmetries, and if we are lucky, it will kind of describe the same physics as the one that we started with. And this is the common theme that happens in many papers in condensed matter physics. No? So you kind of have some Hamiltonian, you have some symmetries. Say I can describe this with this kind of quantum field theory, but it's a bit of magic. Okay, so in many times this works, and many other times it doesn't work. And if it doesn't work, you say, well, then it doesn't work, but you don't really know why it doesn't work. So it's very complicated to get some or to build some intuition there on what is allowed and what is not allowed. And it all has to do, of course, with phase transitions. So if you kind of do quantum field theory, you're basically interested in systems that are at a phase transition. Okay, so this is typically needed for describing systems that have power law decay of correlations that are actually critical, and therefore close to criticality you can have many phases, and a slight perturbation might actually change the physics completely because you are in a different phase. And so one of the reasons that I'm saying this is that certainly for people that are interested in simulating quantum field theories with quantum computers, this is an extremely relevant and important point that actually by discretizing, so once you have your quantum field theory, you say, well, let's go back to some effective many-body Hamiltonian, let's discretize this Hamiltonian and add some terms. Well, depending on how you discretize it, you might actually get completely different physics. Because you're close to a phase transition and actually adding some tiny little terms, because that's what you do when you discretize your system. You kind of change your Hamiltonian a little bit, you add some terms, but you might add relevant terms to it that change the physics completely. And this is actually not, it's not obvious at all how to do this. So if you have an interacting system that is that has no kind of connection, that is not close at all to something that can be described by a free theory, and then you say, okay, let me kind of put this on the lattice and try to simulate this, it's not clear at all how to do this. At least I don't know exactly how to do this in complete generality. So anyway, so also in quantum field theory, all the big problems are about quantum correlations. Okay, so it's exactly the cases where the Hartree-Fock approach does not work. So what is so of course you're all familiar with Feynman diagrams and all this. Well, this is okay for systems in which the Hartree-Fock approach works. Okay, so it means I have some ground state with Hartree-Fock, and then I do perturbation theory on top of it. Well, this perturbation theory is nothing. These Feynman diagrams are nothing more than some way of organizing this perturbative expansion. But then you go to a phase transition and end up in a regime that has nothing to do anymore with your free theory, and then you don't know anymore how to describe this using your perturbative series. And of course that's exactly why in many cases the perturbative approach fails, and that's the real challenge in quantum field theory, is how to deal with the quantum correlations, that cannot be described by free theories. Okay, so is there a clock somewhere? Yeah, okay. Are there any questions about this? Because I'm very general, and I just keep on talking unless I know what you guys want. No, I'm just saying what I find interesting, but if you kind of give me some questions, then I will have a better idea of what you guys find interesting. Okay. Yes?
Can you give an example for this case that you mentioned, the Bally's model gives you something which is different from the clinical practice?
Yes, so I know that, but this is a very specific example, because this is something that some students in our group are doing. It turns out that if you look at the Gros-Neveu model, the Gros-Neveu model is in some sense a very simple 1+1D quantum field theory that has some big symmetry group. And it's not at all, so it turns out that depending on how you discretize it, you really describe a different theory. And this is really because it's not clear at all at priori what are the relevant and not relevant terms there. Okay, and there's some marginal terms involved, and it's a very subtle interplay. But of course, it should not be. So I'm sure that I don't know whether people, maybe Leo knows examples of this, of things of quantum field, depending on how you discretize it, that you actually describe some different phases. I don't know whether there's simple examples of this.
Nothing simple comes to mind.
Yeah, indeed. If Leo doesn't know, then nobody knows.
How do you actually discretize from here?
Well, you so you have field operators, okay, that are described by some commutation relations. Okay, and then you say, well, let me kind of all the field operators in one. Let me kind of say the sum of all of the integral over a small interval, for example, of psi. I describe this with one field operator. Okay, and then you kind of doing this. So Well, it's a technical thing, but actually there's many different ways of doing it, and of course there's many different ways. So you have to discretize. You have to put some epsilon, some lattice constant in it, and the whole thing is that if the lattice constant goes to 0, you should basically get the Hamiltonian of your kind of continuum theory. But there's many different terms that you can add there, such that if this epsilon or this lattice parameter goes to 0, also go to 0. And a priori you don't know which terms you have to include and which terms you don't have to include, such that you will actually end up in the theory that you're really interested in describing. Yes?
You mentioned that quantum correlation is hard to describe in quantum field theory. Is that related to the fact that quantum correlation in QFT is in the space and time, and the usual way to discuss quantum correlation, just for example, entanglement is just in space?
No. So no. If this is what this is certainly not what I want to say. So of course time adds an extra complexity, but already to find, so the big problem in quantum field theory is again to find the ground state. Just what is the lowest energy state, the vacuum, the absolute emptiness is actually the hardest of all. Okay, to find basically to describe what happens in the vacuum of your theory. To find the vacuum is the hardest, and once you have that thing that is nothing, because then you start probing it. Okay, and then you have to probe it, and then of course you have to act. So you have to excite it and look at how these excitations go. But it turns out that all this information is completely encoded in the ground state. Just like I said, if you have the ground state, you basically have the information about your full theory. Well, it turns out that this is the same in quantum field theory. Once you have the vacuum, you basically know indeed what happens. If you can calculate correlation functions in the vacuum, you can basically calculate any thing that you want. And certainly for relativistic quantum field theories, it's in some sense the situation is simpler, because if you know the equal time correlation function, you also know the non-equal time, because it's Lorentz invariant, and you can start kind of doing all these things.
Definitely problems where this is not true, and where the ground state does not encode all the dynamical properties of the excitations. And localization is a famous example, but it's not the only one.
I agree. So I should indeed have put this asterisk there. Yes. I'm mostly, so in these lectures I will mostly be interested indeed in translation invariant systems, and there that are in some sense have a relativistic description, and there it's true. But certainly, indeed, I should certainly have said this. I agree. I completely agree with you that there are cases in which the ground state alone is certainly not enough to describe your all the excitations. Of course, there could also be kind of competing ground states. There's other cases in which things can happen. No? That there's like two competing ground states, and one is a little bit lower than the other one. Also, there you don't have any idea of what is going on in the thing. So, yeah, sure. Yes.
So about this topic, so you mentioned the importance of some kind of constraint, like to locality. That allows you to get all the information about the excited states. So you mentioned something. Can you expand on this?
Yeah, we will. I will come back to this later. I will come back to this later when we actually talk about tensor networks, in which you will be able to build the particles in a theory starting from the vacuum. So, so this is indeed not the situation that like this localization, but somehow more the situation, the standard situation in which you have like a translation invariant system. You find a vacuum, and then you're interested. Okay, what are the particles now in this theory? So, what is actually a particle from the point of view of yeah? What is this? Is not an obvious. This is not obvious at all. No, what a particle is. And a particle is some kind of an excitation on top of your vacuum. And how do you describe this? Okay, what are the features there? And you will see that there's some effective. There's a very, using these tensor networks, there will be a very simple way of understanding what they are, but this is something that of course is independent of these tensor networks. So particles or the excitations will somehow be plane waves on top of some of your background, and these plane waves live in some effective theory, and you will be able to describe this. Yeah. No, but so just to give you an idea of why indeed. So the simplest way of understanding that the ground state gets information about your excitation is just that if you have the ground state and you calculate the correlation functions, okay, then you know basically how they decay. Well, then you know the gap in your system. Okay, because you know that the correlation functions decay like somehow the correlation length is directly related to the gap in the system. Okay, so if you know the correlation functions in the vacuum, you basically know what the first excited state has to be, because you know what somehow if you look at the correlation functions. So this is the simplest way of already seeing that indeed the ground state encodes all this information, and you can elaborate on that, and you can actually build on this to be much more precise to get these things. But we will do this later. Okay, so let's. So I have lots of blackboards for very few formulas. So let's continue in the same vein. So we have quantum many-body physics. Okay, so we have like lots of degrees of freedom. Okay, so again, I think I'm just repeating things that you have already seen either in school or somehow in these previous lectures. But anyway, so the really interesting thing about quantum many-body physics is indeed the fact that this phase space, or the degrees of freedom in your system, increase exponentially with the number of spins or the number of electrons or the number of whatever you want. But the interesting quantum many-body physics, or also classical many-body physics, because as I said, it's not entirely clear how quantum many-body physics is so much richer than classical many-body physics. That's actually, so the interesting physics comes along when there's a competition between different terms in the Hamiltonian. Okay, so or there's a competition between different things in your system. Okay, so again, to go back to classical statistical mechanics. So why do you have phase transitions at all? Okay, why do we have phase transition in water and ice and so further? It's really because in nature there's a competition there between energy and entropy. Okay, and whenever you have competitions between two things that are incompatible with each other, so if you make one larger, the other one has to be smaller, and then you tune the importance between these two, then at some point you will have to go to a phase transition. So this is exactly what is happening in classical stat mech. You have, like, you want to minimize, the equilibrium statistical mechanical physics is about minimizing the free energy of your system. So you have a Hamiltonian and you have some entropy in the system, and the temperature is controlling the weight that you associate to either the energy or to the entropy. So the larger the temperature, the more weight you associate or attach to the entropy and less to the energy. And if you think about something like an Ising model where all the spins want to point in the same direction, if you want to minimize the energy, there's clearly a competition between these two. If all the spins point in the same direction, then the entropy of the system will be basically zero. Okay, because there will now be extensive entropy in the system, because all the so if you want to minimize the energy when all the spins up, then the entropy will also be minimized. But you want to minimize the energy and maximize the entropy. And now by tuning this parameter, or the temperature, you will you will say that the entropy has to become more and more important, and at some point the entropy will win. And this is exactly where your phase transition is in the system. So it's a competition between two different things. So this is one of the points where quantum many-body physics becomes interesting. It's by adding thermal fluctuations. Okay, so by adding a temperature to the system, you want to have fluctuations, and these thermal fluctuations will kind of give interesting physics, will give rise to interesting physics, and also to quantum phase transition, or quantum actually classical phase transitions. It doesn't matter. So it's phase transitions between the different phases. So this is the first possibility of having interesting physics, just some thermal fluctuations. So the second way of getting interesting physics, and this is also purely classical, but can also has, of course, a quantum counterpart, is actually to add frustration in the system. So if you have something like a Kagome lattice, or some triangular lattice, and you want indeed, and you have an antiferromagnetic Ising model, so the spins want to be anti-aligned, the nearest neighbor spins want to be anti-aligned, then clearly on every triangle there will be some frustration. Okay, and whenever you have some frustration of that kind, turns out that there's interesting physics coming along, because this will give rise to kind of an exponentially large ground state manifold, and but with some very peculiar features, because what you will have is that on every triangle or any plaquette, you will want to have two spins. Well, you will never want to have three spins in the same direction. There's always two spins up and one down, or two spins down and one up, and this gives rise to some very non-local correlations in the system, because there's this frustration will give rise to some in some sense some topological features of your classical stat mech model. Okay, and this is actually a very interesting feature, and and actually has also very real life has real life applications. So one of the most amazing examples of such frustrated systems was an extremely nice thing that was observed first by Pauling, the chemist that got the Nobel Prize a long time ago. So what he observed is that if you look at ice, I'm not so sure which ice, but I think it's the normal ice like you have in water. But there's many different types of water ices. But anyway, so there's one of these ices, and if you cool this down all the way to zero temperature, then you could basically calculate the residual entropy, the entropy in this thing. And what he realized, or what people had realized, is that this was not zero. Okay, so there is some residual entropy there if you just have ice. Okay, and this is in violation with thermodynamics at first, you would think. And it has to do with the fact that you have all these tetrahedra, and he came up with a very simple stat-mech idealization of this, in which he could indeed understand that this residual entropy has to do with some frustration. The fact that indeed these spins, and every tetrahedron you have kind of to have 2 spins up, 2 spins down. This basically means these spins is an abstraction of where do you put the hydrogen atoms next to the oxygen. So you have H2Os, all kind of tetrahedra, and you have to map them on some parallel core lattice. And it turns out that indeed this residual entropy is nothing more than counting. It's a combinatorial problem. How many different ways are there to put all these hydrogen atoms such that somehow next to every oxygen there's 2 hydrogens close and 2 far, and how many different ways are there to do this? And this frustration gives rise to very interesting physics in some sense. There's some long-range correlations, there's some effective gauge theory that emerges there because of these local conditions. So this is certainly one of the ways in which you can have interesting physics. So it's frustration. So first we have thermal fluctuations. Second, you have some type of frustration in the system. Okay, that gives rise to some ground states. So to an exponentially large ground state manifold. That's typically the hallmark of a frustrated system. But in such a way that all these different ground states are in some sense very non-locally. They're non-local because there's there's some notion of gauge conditions that tell you that locally you have to obey this spin ice rules for this specific example of ice, and it turns out that this gives rise to this correlation. So if you write down the thermal Gibbs state for this particular system, what you will see is that indeed this is it's a very non-trivial model that gives rise to long-range physics. And then you can start. This is a purely classical stat-mech model. Then you can start saying, okay, what is the quantum analog of this? And you will be able to define entanglement Hamiltonians, and you will see very interesting features. You will see kind of CFTs emerging and all this physics just by looking at this second way of introducing a competition between these two terms. So quantum ManyBody physics is all about competitions between different terms in your Hamiltonian or in your kind of system. So the third way of getting interesting many-body physics is, of course, by introducing another way of frustration. That's namely by introducing quantum mechanics. Okay, so by going to the quantum regime, because the 2 previous things that I said are actually purely classical. But the third way of doing this is by for introducing some notion of frustration is by doing quantum mechanics, in which you kind of you get a competition between the different terms in your Hamiltonian because they don't commute. Okay, so this is, I think, for this whole audience, probably by far the simplest way of understanding this. So, for example, let's take the Ising model. Okay, so the quantum Ising model has different terms in the Hamiltonian. So you have some terms like sum over ij zi zj. So this is basically some, maybe with a minus sign or a plus sign. It doesn't really matter. Whether in one case it's ferromagnetic, the other one it's anti-ferromagnetic. So you have two levels, like a two-level system on every side. And this term in your Hamiltonian wants to kind of basically align or anti-align all the spins that are next to each other. And let's actually, for this particular case, just look at the one-dimensional chain in such a way that there's no geometric frustration. Okay, so you just have a one-dimensional line, and you have a Hamiltonian like this. But then you also have, so you kind of put some p-factor, but then you add a term, namely a magnetic field in the transversal direction. So there's no frustration whatsoever here. This is a trivial Hamiltonian, but now you add terms to this Hamiltonian that don't commute with it. And that's the whole point. Now you have a competition between somehow J and B, And depending on how large J and B is, one will win or the other one. It turns out that for this particular case, this is completely analogous. So there's really a one-to-one mapping that you can do between this model and these thermal fluctuations for the classical Ising model, in which this B would basically be somehow the temperature. This would kind of tell you what the entropy is in the system, and this would tell you what the energy is. And the competitions between these two things gives rise to phase transition. And indeed, the phase transition that this model has, when, in this particular case, it's when J is exactly equal to B, there's a phase transition there, is really completely analogous. It's actually exactly the same, can be described by the same field theory as the classical Ising model. But we will kind of become more precise about this very soon. So anyway, so the point that I wanted to make is that there's three ways of getting interesting many-body physics: thermal fluctuations, frustration, and quantum fluctuations. And it turns out that, of course, all these ways, so these tensor networks will be very kind of well suited for giving insight in all these different aspects. So it's about competition between different terms. And where I want to go now is to see what the effect is of these different competitions or on this so what are the manifestations of the fact that there is a competition there in the possible reduced density matrices of ground states of such systems. So I'm sure you have had already lots of talks about reduced density matrices and their properties and the disentanglement properties. Well, what I would like to study now is I would like to get some insight in what the possible reduced density matrices can be of systems like the Ising model, but also, of course, of more complicated systems like the Heisenberg model in general. Okay, so let's indeed look at this Ising model. Let's assume that it's translation invariant in one-dimensional, so it's a quantum spin chain. So this is interacting between all nearest neighbors, only the nearest neighbors, and this is acting on all spins, and it's completely translation invariant. So let's try to make a picture of what the possible or what the reduced density matrices of ground states of such systems could be. So what I would like to plot to make is basically a plot of, so what is the ground state of such a system? So the important thing is that the ground state of this system is just the system that has the lowest possible energy. Okay, that's of course pleonasm. There's no information in this thing, but the important thing is that, of course, because this thing is translation invariant, is Hamiltonian. It's easy to see that if you have a system with a unique ground state, so a unique extremal eigenvector or value, then this eigenvector must inherit all the symmetries of your Hamiltonian. So this is a very easy exercise in linear algebra. If you have a symmetry, you have a Hamiltonian that commutes with a certain symmetry operation. So, for example, this symmetry operation could be the translational, the shift operator, in which you shift all the spins to the right. That indeed the eigenspaces corresponding to this Hamiltonian must exactly have the same symmetries. And if this eigenvector or this eigenvector corresponding to a certain eigenvalue is unique, that means that this eigenvector must indeed have the same symmetry as your Hamiltonian. So there's a little caveat. It does not mean that the ground state has the symmetry of your system. It could be that if you have a degenerate ground state, could be that not a single ground state, so it's only basically the subspace spanned by these two ground states that has this symmetry. Okay, so you could have situations in which, for example, the ground state would be like dimerized. I have like dimers like this, or somehow I shift them all by one side, all dimers, and so both of them don't have the translation invariance, but somehow of course the subspace of both of them together has the right symmetry. But anyway, so in this particular case, we are interested in systems that have a unique ground state. So what we should look at is at basically the set of all possible translation invariant wave functions. And this will turn out to be a very fruitful way of thinking. as we will do later in this first lecture, we will try to understand indeed what is the structure of wave function that have some symmetry, namely translation invariance. How can I, in a general way, write down wave functions with such a symmetry? Okay, that's a very, just think about it, it's a very complicated thing. It's very non-trivial to write down generic wave functions that are translation invariant and are not trivial. Of course, it's trivial to write down all spins up or all spins down or something like superposition of all spins up and all spins down. This is translation invariant. But to go beyond this, well, maybe you can do some plane wave, so like a superposition of all zeros and one all spins down and there's one spin up, and then you take the sum of all these things. But beyond this, it's very complicated to get an idea of what these wave functions are. And it's exactly that exercise that will lead to this whole kind of set of tensor networks. These tensor networks are in many ways the simplest way of constructing generic families of wave functions that are translation invariant by construction. Okay, so this is, and we know that this is what is needed because ground states of such systems must have these symmetries. So it means that if you look at the set of all possible wave functions that are translation invariant, okay, so I'm only looking at the set of all translation invariant wave functions. So translation invariant means I kind of I have a one-dimensional system, and if I shift the wave function, it's equivalent to it up to a phase. Okay, let's allow for some phases if you kind of apply a shift. That will be some momentum. Basically, this would be the momentum operator, but that's not very important. Let's look at the set of all possible translation invariant wave functions, and in particular, let's look at the reduced density matrices of all these possible wave functions. Okay, so in this particular case, because the Hamiltonian only has nearest neighbor interactions, so I'm only interested basically in the nearest neighbor. So let's write rho 2 as the reduced density matrix of this full wave function. The reduced density matrix on two spins. In this particular case, this would be basically a 2-qubit reduced density matrix. Once you have this reduced density matrix on these 2 qubits, you can trivially calculate the energy, okay, because the energy is obviously only dependent on the nearest neighbor correlations. So that means that, because we already know that there's interesting physics there, that the physics describing possible reduced density matrices of translation invariant systems must be very interesting. Okay, so the question of finding what are all the possible reduced density matrices of translation invariant systems is an extremely non-trivial question. It's a very non-trivial problem. And actually, if you solve this problem, if I would give you a characterization of what all possible reduced density matrices of translation invariant systems would be, I would automatically have solved all the possible. I would be able to determine the ground state energies of any possible Hamiltonian on 2 qubits with nearest neighbor interactions. Okay, because if I have an efficient way of describing this set, I would just say, okay, let's try to find the element in that set of all possible reduced density matrices that minimizes the energy, and the energy is only dependent on this one 4x4 matrix. Okay, so this is, of course, not surprising from the point of view of linear algebra. This is the dual problem. Okay, finding the set of all possible reduced density matrices of translation invariant systems is equivalent to finding all the ground states of translation invariant Hamiltonians. Okay, this is kind of in one-to-one correspondence. Nevertheless, it's very illuminating to study this convex set. So how does this set look like? How do these reduced density matrices look like? And also to try to start thinking about entanglement there. Okay, so for example, because we know a lot about reduced density matrices of 2 qubits, we know exactly how to characterize when they are entangled. I'm sure you have seen this in many of the lectures in the first weeks. So to describe entanglement of formation, entanglement of distillation, all these kind of things. Well, what does that mean for these things? What does it mean when will there be entanglement? Well, when will it be kind of separable? Well, it turns out that indeed is separable. These things will be separable. Separability will be basically when the mean field theory is exact. And whenever we go beyond mean field theory, you will have entanglement. Okay, so the fact that indeed there is interesting physics in this is all to do with the fact that already your local reduced density matrices exhibit entanglement. Okay, there will be, because if you don't have entanglement, well, then the ground state of this thing will actually be trivial in the sense that it will be very close to a product state. So anyway, so the problem of the quantum many-body problem certainly the ground state quantum many-body problem. And again, indeed, localization, all these things are, you have to be careful, but I'm talking about the quantum many-body problem of a system of translation invariant systems. Is all about find a way of describing what the reduced density matrices can be of this system. And it will turn out that the reason that these tensor networks will work very well is that these tensor networks give you a way of approximating these reduced density matrices in a very systematic way. So the way you will be able to, so the complete set of all possible reduced density matrices of translation invariant systems will be very close, will only be kind of marginally larger than the possible reduced density matrices of translation invariant tensor network states with a certain kind of efficient description. Okay, and that will be somehow the reason that you will be able to break down this exponential wall in which you start with a problem here that is actually exponential in complexity at first sight to the problem that actually is has a polynomial complexity. Okay, so let's try to play some game and indeed kind of try to plot here expectation values. So I will plot somehow an expectation value of ZZ here, and I plot an expectation value of X on this axis, and I will have to plot actually an expectation value of Z on this axis. So let's try to understand indeed what are the possible reduced density matrices of any possible state that is translation invariant. So every state will correspond to a point here. So I have a certain state, well, it has a certain reduced density matrix. Of this, the reduced density matrix, I plot basically the expectation value of ZZ, of X, and of Z. And let's try to see how this convex set looks like. Okay, and out of this picture, you will be able to deduce all the physics that there is to know about somehow the thermodynamics of your many-body system. So, but for this, I cannot do this on the blackboard. I need some, I would like to do this with my computer. Okay. Okay. So by the way, this is actually so what this whole point of view of reduced density matrix and do quantum many-body physics, starting reduced density matrices is very, very close in spirit to the original way in which Gibbs and Maxwell looked at thermodynamics in the beginning and at the end of the 19th century. So what they have, so if you are ever in Yale, you should definitely, and there's physics building in Yale, on the first floor there is this model there. And this is actually a beautiful model. It's very, very much related to what we are talking about here. So this is like, make a possible plot of all possible reduced density matrices of your system. Well, it turns out that instead of, so when I plot here ZZ, Z and X, well, X of course doesn't have a meaning in classical stat-mech, but you replace this with entropy. Okay, so it's just the entropy. So every probability distribution has a certain entropy associated to it, a certain energy and a certain, well, magnetization. Well, you plot this, well, you would get exactly these convex sets. Well, this is of course much, this is, I'm not so sure, I think this was for water also. Well, anyway, for a complicated substance, and Gibbs made this as a present for Maxwell and then sent it. It was a big deal. Anyway, it's a beautiful picture, and this, we are trying to do somehow a simplistic way of this, but for the quantum case. So if you plot, so let's first look at the zero-dimensional case, okay, in which you only have two spins. Okay, I have two spins. But translation invariant doesn't mean anything, it just means that it's a permutation invariant then. And let's look at the possible reduced density matrices of this system. Okay, so when I plot here, it's basically the expectation value of Z. What I plot here is the expectation value of XX. So you see that somehow this lower, so this is a three-dimensional plot now. So the lower kind of case is basically some ellipsoid. So this thing is lying on the plane when your magnetization X is 0. Well, actually, this is about X and Z, so you should replace X and Z there. Okay, so so this is just well, of course, completely equivalent. Doesn't matter how you do it, but this is the XX, Z, and if this expectation value of X is 0, well, then you really there's no magnetization. You have this ellipsoid, and then this thing is kind of lifting out of the plane. So maybe this is not entirely clear, but you have some ellipsoid, so like this, and then there's this thing lifted out of the plane, and this is the convex set of all possible reduced density matrices of a system with 2 spins. Okay, so the many-body problem will now be.
Is this the reduced density matrix for the ground state of that?
No. Of any possible state. So indeed, good that you asked me. This is a scatter plot of all possible states of 2 qubits that are permutation invariant.
What does the line define?
Sorry?
What does this like a trajectory define?
Oh, this trajectory doesn't mean anything. They're just they mean something, but it's irrelevant. It's a convex set. So this is a convex set. This green thing is basically a plane, is some kind of a plane in which, well, it's you don't have any real kind of. So this is really a plane on top of it, and this is curved. So these blue lines just mean that there's some kind of curvature there. Okay, so you have some ellipsoid, and then some tilted plane on top of it, and in between there is some curved. These blue things are nothing more than curved things. And the question is now, when I go to a system that is translation invariant, it's obvious that the ground state will not anymore. So the extreme points of this set will be the ground states of all possible Hamiltonians that you can form with terms like ZZ, X, or in this particular XX, X, and Z. Okay, so the extreme points of this convex set will correspond to the reduced density matrices of any Hamiltonian that has a linear combination of these 3 terms. Okay, because of course, if you have a linear combination of these 3 terms in your Hamiltonian, the energy, kind of surfaces of constant energy, will be hyperplanes in this 3-dimensional system, and this 3-dimensional plane, and you want to push this energy as far out as you can from the origin, and the way, so you kind of form alpha times x plus beta times xx plus gamma times z. This kind of determines the angles of this hyperplane, and you want to ask, how far can I push this out such that it just touches this convex set? Well, where it touches it, this will be the ground state of your system. And the whole question of many-body physics is now trying to understand how does that picture change if I go to, instead of 0 dimension, to 1-dimensional system? Because how does that change if I add frustration to the system? That's what I was saying before. No, it's all about frustration. So how does that convex set basically shrink? Because it has to shrink, because of course the reduced density matrices of a system with additional symmetry has to be kind of smaller than this. So this convex set will kind of lie inside this. So you go to 1 dimension, and you get this picture. Okay, so indeed this is lying inside that original convex set, but the extremely interesting feature is that there's a whole new kind of surface arising here, namely a ruled surface. Okay, so if you kind of look at this possible reduced density matrices of your of all possible states. So again, so this is, take any state that is translation invariant, plot the expectation value of x, x, and z. So x is this upper dimension, these. So this corresponds to a point here. Well, all these possible reduced RDMs form a convex set, and the extreme points of this convex set are in 1-to-1 correspondence with the ground states of Hamiltonians that have terms of this kind. Now the amazing thing that happens here is that, so it's all about, so what this is, it's about the geometry of Hilbert space. So I look at the reduced density matrix of all possible translation invariant states, and I get an extremely non-trivial geometrical picture, namely that there's a discontinuity here in this description. So I'm not talking about Hamiltonians here, no, I'm just talking about reduced density matrices of states. It turns out that at this point, so here it's nicely curved, but here it's really completely flat. So it's a ruled surface that emerges, and this is exactly where your phase transition happens. So this is exactly here, this point here would exactly correspond to the point where j is equal to b. Yes?
X refers to the nearest neighbor, XX?
Yes, only nearest neighbor xx. But of course you can do this for any, this is just one example. You could in principle do this for any Hamiltonian. You can do this for the Heisenberg model, for any possible, the Hubbard model, whatever. But the really interesting point of view, and this is really the point of view that comes from this quantum information theory. So, in some sense, the fact that there are phase transitions in many body systems has nothing to do with Hamiltonians, or of course it has to do, but the real kind of the reason that there are phase transitions at all is because of the geometry of your Hilbert space, the geometry of the possible reduced density matrices of systems or of wave functions that have a certain symmetry. Okay, and already there, the full richness of the thermodynamics of quantum of many body systems is already present there. So what happens here is that there's a ruled surface that is parallel with this x-axis. So how can you understand now spontaneous magnetization and all these kind of things? Well, spontaneous magnetization means, so as we said, if you have a Hamiltonian, for example, this one that is written there would be a linear combination of terms like this and this, but it would not have any terms like this. Okay, so hyperplanes with constant energy would be parallel with this axis. Okay, so it takes such a hyperplane with a certain combination, and you say, okay, let's try to push this out from the origin as far as I can until it touches my convex set. And what you will see is that there's a very different behavior here and here. If you're in this regime, this is basically a paramagnetic regime, you will only touch this one point here. Okay, because it's parallel with this, you will kind of have an extreme point, you will just touch here. But once you are here, this hyperplane will basically touch a whole line of your convex set. And that means that if you would add a tiny amount, an epsilon amount of energy x, this would tilt this Hamiltonian, this hyperplane a little bit in this direction, and immediately the magnetization would be here. Okay, because it's parallel with it, so you're really lying on top of it, and you perturb it a little bit, it would kind of get a tiny angle, and you would get a spontaneous magnetization here. Well, this is actually the absolute value of x now, but so this is in some sense the way. So that this is the way to understand the physics of this Ising model and the spontaneous magnetization and the fact that you have phase transitions. Phase transitions have to do with points where this convex set becomes irregular or somehow non-analytic, or I don't know, in many, yes. It turns out that, for example, this, well, maybe let's first take a question. There was a question somewhere, yes?
So the blue lines, those are pure states, and the green area, those have to be mixed states?
Yes, this is actually, so indeed, somehow, if you're in the symmetry broken phase and you want to have this point, the way to get this is actually indeed having a mixture of a state with expectation value x, let's say 0.6 here, and minus 0.6. And the convex combination of this would indeed correspond to this state. And that's, of course, not an extremal state of this convex set, but it is the Gibbs state. So it means that indeed Gibbs states of your Hamiltonian are not necessarily extremal states. Because if somehow you have something that lies here, then actually you would have a spontaneous magnetization about this. So actually for the people, maybe there's people here interested in foundations of quantum mechanics and how quantum computing could kind of really give you new insights into this. I think, so this whole picture is very relevant for this. So the fact that actually in nature you have spontaneous symmetry breaking, that nature chooses this point and not this one, is exactly equivalent to somehow this collapse kind of point. Why does indeed the wave function collapse so why can't you have cat states? Why don't you indeed have a superposition of this state with magnetization plus and minus such that you would there? No, nature chooses one of them, and indeed that's what gives rise to basically somehow the fact that you have, so the fact that you have spontaneous magnetization, the mystery there why nature chooses this is the same as the mystery of why you have, well, it's the same of the mystery of the measurement problem. Yes?
So, can I think of this as the flow of the reduced density matrix under renormalization?
It's tempting, and I will give you a picture of this. So I will give you a picture of this, like for Bose-Einstein condensation, exactly the same kind of thing. But anyway, so probably people are asking on the other, why is he saying this? It has nothing to do with tensor networks and all this. Is that the question you wanted to ask? No. Okay.
I had a question. So you get sharp features in this set if you consider an infinite chain. I suppose that if you go to finite chain, these become smooth. I was wondering, can you quantify the sharpness somehow?
Yes. So we have been looking at this. I don't have a definite proof. I would be very interested if somebody would want to work on this. I think this curvature here becomes exponentially small in the system size. But somebody should actually prove this. I think it is exponential. So at every finite length, you don't have, this is still a little bit curved.
But I presume you obtained it by doing a 20-site.
No, well, the Ising model, well, actually we do this with, we obtain this data by tensor networks. It's not easy at all. So you would think this is the Ising model, so it's exactly solvable, but that's not true, because you have also this additional field that is longitudinal, and it's not exactly solvable anymore. And so what we did is basically, or what my student did, Valentin Zauner, is do millions of ground state calculations for all possible Hamiltonians, and then you find the ground state, you kind of calculate the reduced tensor matrix, this is a point. And these points, so the nice thing of course is that these points give you automatically the extremal points. The extremal points of this convex set are exactly, or a one-to-one correspondence with the ground states of your local Hamiltonians. And indeed, in this whole region you don't see anything, you only see these points, or somehow if you would have also minus x, the other kind of, the ones on the other side. Okay, so let's go to higher dimensions. So I think one of before we do this, what is this upper plane? So this upper plane is something that is usually not kind of discussed at all if you talk about the Ising model. So can anybody guess what this upper plane would be? Because there's also so it's clear whenever you have this green things, this is a ruled surface. It's like a plane there. Something interesting has to happen. So it has to do with interesting many-body physics. So there were three ways of getting interesting physics. No, you could. Well, it turns out that this upper plane is exactly one of these cases when you have frustration. Okay, when the ground state actually has an so if turns out that if you write down an antiferromagnetic Ising with a magnetic field, with a term, so J is equal to 1, B is equal to 0, and C, which is basically the term that proportional to Z is equal to 2, you get frustration. You get a non-trivial frustration, and all the possible ground states of the system will turn out to be the ones that correspond that obey the rules of the Fibonacci chain. If you have a spin up, it has to be followed by a spin down. You can have as many spin downs as you want. If you have a spin down up, it has again to be followed by spin downs, and this will form now the Hilbert space of these systems. And somehow, if you don't have a B, you just have this situation. Well, this is exactly this upper plane. So this upper plane will characterize basically this whole frustrated kind of ground state manifold. And then adding a tiny perturbation somehow will mean that you lift this plane a little bit and you will end up somewhere on this. So for people that have seen all this physics about the golden chain, so there were lots of papers in the last years about anionic chains in one dimension, all this. This is exactly what you get. So you must start from some situation that is purely classical. So there's no term here. So there's no quantum here because everything commutes, but you kind of tune these parameters B, A, and C in such a way that you get a frustration, that you get an exponential degenerate ground state manifold. This is basically described by this plane, and then you add somehow the other things as perturbations. Now you can add a tiny B, or you can change the J infinitesimally or C infinitesimally, and this will give rise to all this physics of these anion chains. This determines the Hilbert space of your system.
I thought they impose a constraint on the Hilbert space. That's how they do it.
Yes, well, indeed, they impose a Hilbert, but how do you do this? Well, this is a way you can actually do it. So if you would like to do the experiment, well, you would do it. I don't know whether you can make a Hamiltonian like that in an experiment. I don't know anything about experiments, but I'm sure, like with atomic physics or with optical lattices, they might be able to do something like that. That gives you an explicit way of finding this Hilbert space. So indeed, this was always confusing to me. They have this anion chains. Their Hilbert space is the space of the anions, but where do you get this from? What are the microscopic degrees of freedom? Because there are no anions in nature, no? So, and this is the way you can get it. You start from some frustration, and then you just what is the connection with tensor networks? Because that is probably not clear at all. It will turn out that tensor networks will give an extremely good approximation of this convex set, and for this we know better. So how well? So what we'll have is that you will approximate this convex set using tensor networks actually from the inside, okay? Because instead of the possible reduced density matrices of all possible wave function, you will only look at wave functions that can be described efficiently using a polynomial number of parameters. And the question is then, for a variational method, how good does it do in general? Well, it's about how good can I approximate this convex set from the inside. And the distance between the inside and the exact convex set, so you can measure this with any measure, with any kind of metric that you want, will actually be polynomially small in the number of variables that you have in the system. And that's a clarification that actually justifies why indeed these tensor networks will allow you to break down this exponential wall to in such a way that you get the polynomial kind of description. But actually, before we do this, there's really an interesting exercise now to go to higher dimensions. So you could ask so we went to 1 dimension now, what happens now in 2 dimensions, what happens in 3 dimensions, 4 dimensions, and so further. What happens with this convex set? So all these convex sets have to form some kind of a series of Russian dolls. They all have to fit into each other. Okay, it's like the first one would be Putin, the second one would be Trump, and so further. They would all kind of be smaller and smaller. And so they would all fit into each other. And at some point, it will be interesting to understand indeed where does entanglement play a role. And you will see that indeed in infinite dimensions. So when the dimensions of your system will become infinite, there will be no entanglement whatsoever anymore. So this convex set will just be the convex set of all possible reduced density matrices that are separable, that have no entanglement. This will turn out to be equivalent to mean field theory. And indeed, that's why most of the interesting many-body physics arises in low dimension. Actually, if you want to have strong quantum correlations, it's better to work in lower dimensions. The lower the dimensions, the stronger the quantum correlations will be. Because the higher the dimensions, at some point, these convex sets will become indistinguishable from the convex set of mean field theory of separable states. And that means that actually then you don't need entanglement anymore. The entanglement is just 0. Okay, so the lower the dimension, the more entanglement there will be in the system. And you can see this actually from these convex sets, as I will, yes.
What's the intuition behind it?
Sorry?
What's the intuition that for infinite case it will be separable?
This has to do, if you have like, but I wanted to talk, but if you have a cubic lattice, like you have a line, okay, what happens in 2D? You have a square lattice. In 3D, you have a cubic lattice. We know that the ground state must have all the symmetries of your system. Okay, so that means that if I have a cubic lattice and my reduced density matrix between these two is something, this reduced density matrix has to be the same, it all has to be the same. So that means that if there's entanglement here, I must have the same amount of entanglement here, and there, and there. And as you have seen, there is some notion of monogamy of entanglement. And if I have a very large dimensional space, which I have many, many neighbors, well, then of course, if I have to share basically one E-bit with n neighbors, well, at most I will have 1 over n entanglement with each of them. And if n goes to infinity, or the dimension of your space goes to infinity, it has to be 0. So it's really a consequence of the monogamy of entanglement. The fact that if you have a reduced density matrix like here and here and here and here, they all have to be the same. Well, the more you have to share entanglement with, the less entanglement you can have, and at the end, mean field theory will come into play. And of course, this is extremely well known in classical stat mech, that there is an upper critical dimension. Okay, there's an upper critical dimension at which somehow these critical exponents become the mean field critical exponents. And this is really when this convex set has shrunk in such a way that indeed all the features of this convex set are basically the same as the features of the infinite dimensional case. I didn't really say this, but the speed at which this thing goes up here. So this is some curve that goes like this. The speed at which this goes up is of course the critical exponent. So out of this you would immediately be able to, if you see this picture, you would immediately be able to deduce that the magnetization, or the critical exponent for the magnetization in the Ising model, is 1/8. Okay, so this is basically the distance from this that kind of increases like a 1/8. So all this information is in this picture. But let's go to 2 dimension. Immediately to infinite dimensions. So this is actually the convex set in infinite dimensions. So you see, this kind of region grew, this kind of shrunk, but this is still completely inside this other kind of convex set. And this blue line here, that is here, is actually the original red line. So this red line that you have here turns out to be a line of product states. So there's a particular combination of terms in your Hamiltonian of x, c, and x, so that the ground state is exactly a product state. Well, of course, this product state will still be there if you are in infinite dimensions. And indeed, this turns out to be the phase transition. This is exactly the line where you have of the phase transition between the paramagnetic and ferromagnetic case for an infinite dimensional Ising model. Okay, so let's kind of look at them all together. So this was 0D, 1D, infinite D, and somehow everything in between. You just have to interpolate between these two, and you get basically 2D, 3D, and so further.
When it's like the dimension larger than 1, do you assume that it's like an isotropy in all directions, just 2 sides?
Sorry, what is the question?
So when the dimension is higher than 1, when you're choosing two-side reduced density matrix, you just assume that it's isotropic in all directions.
Yeah, but we know that we can do that. Okay, with those of the lots of generality, we know that the ground state of your full Hamiltonian must inherit all the symmetries of your Hamiltonian
So in isotropic models.
in isotropic models. So how did we obtain this convex set? Because you say, well, this is maybe very complicated. There's no to calculate this. Well, it's actually very simple. You just plot the possible reduced density matrices of all possible separable states, and for a separable state of 2 qubits, we know that it is completely characterized by semi-definite constraints. So I think you must have seen this partial transpose criterion and so further in your lectures. Well, this is exactly how you plot this. You say, let me kind of try to minimize the energy of my Hamiltonian under the constraint that my 2-qubit reduced density matrix is separable. Okay, so that's the only thing. You don't have to do any many-body calculation. You just say, let me look at all possible separable reduced density matrices, and let me minimize the energy with respect to a certain Hamiltonian. Well, that's a semi-definite program. You solve the semi-definite program, and you get this convex set as an exact solution. So indeed, this upper plane is still exactly there. So let's see, what else is there? That's the picture for the 2D classical one. So it's exactly the same. So this to me was amazing. So this is one of these manifestations why classical is basically the same as quantum. So the only thing you do here is replace this transversal magnetic field with entropy, and you get exactly the same picture. It's really a one-to-one picture. So you just replace this. All the physics is the same. So you get this upper plane here, you get the kind of paramagnetic phase, ferromagnetic phase, critical exponents, these kind of things is the same. This is basically, so this is take any possible probability distribution in the world, calculate the entropy expectation value of z, this is a point, plot all of them, you get this convex set. So this is really the analog of what Gibbs and Maxwell did. Then you can, well, they had to take the convex hull.
But the picture you showed at the beginning.
Yeah, but they should have taken the convex hull of that picture, because that's, you know, in thermodynamics you always get these things. But of course, so they calculated this using equations of states. And these equations of states you always have to, like this, what is it called, this van der Waals kind of pictures, you always have to take the convex set now. So the real thing is the convex, but they knew this, of course. So this is, so it's interesting. So if you have a Potts model, well, there's actually a new kind of frustration system here, but then you go to q equal to 5, and then suddenly instead of a ruled surface, you get a whole plane. So this is now a full plane that is parallel to kind of your thing, and this is a first order phase transition. So I didn't really explain the difference. So, but this phase transition that we saw before were always second order phase transitions. What you have here, if in this convex set for q equal to 5 Potts model, you actually get a whole plane that is kind of completely, it's not a ruled surface anymore, it's really a whole plane that is there in this convex set. And then it means that if you have a certain Hamiltonian and you change the terms, you will have jumps. You will have discontinuous jumps of your terms, because this is a whole plane. You kind of add a little perturbation here or here. You have, and this means that indeed there's first order phase transitions there in the Potts model. So of course there's also completely equivalent things for the classical kind of stuff. Just to give you an idea, because we are in GILA, we have to talk about.
This is the physics department?
Yeah, but isn't that all the same? You're affiliated to GILA. But GILA and physics is different?
Yes.
Okay. Okay, I didn't know that. Anyway, Bose-Einstein condensation is exactly the same picture. Okay, so you plot expectation. So you just take free. So this is of course the simplest case for free. It's just Bose-Einstein condensation with a free system. So you just take kinetic energy, entropy per site, expectation value of your order parameter. You plot the convex set of all possible reduced density matrices that you can imagine. At some point, there is a ruled surface emerging. That's where your Bose-Einstein condensation occurs, and where your expectation value of psi acquires somehow a non-trivial expectation value. Okay, so I think this is to me at least this is very revealing. What it shows you is that indeed these order parameters and all these kind of things, it really has to do with the geometry of possible local reduced density matrices. Okay, this has to. So I'm not talking about Hamiltonians here. I'm just talking about what are all the possible reduced density matrices. This is actually for a fixed density that I plotted this here. Well, you get all this. So I think there's another picture that I wanted to show you. Actually, this one. This one is actually also very interesting. So this is actually when you plot. If you have a Hamiltonian, that is the Heisenberg model. So how much time? I'm going very slow, but okay. So if you would have a Hamiltonian, there's like xx plus yy plus delta times z. This turns out to be probably the most studied Hamiltonian by people that are interested in integrability. So it's like you have some xx term, yy term, and then some parameter delta and zz term. So this was basically this describes the interactions of your electrons. This is basically the kinetic energy. So indeed, if you would take a field theory, you would see that these terms correspond to the kinetic energy. This term corresponds to the interaction between the electrons. And this is actually the most, well, this is a very physical Hamiltonian. And if you start from some electrons and on a lattice, and you try to find indeed what are the low energy degrees of freedom, then by some simple perturbative arguments, you come up with this Hamiltonian. So this is an effective Hamiltonian for describing electrons hopping on a lattice. It doesn't matter in 1D and 2D, whatever. So this turns out to be the Heisenberg model, and the Heisenberg model is actually when this delta is equal to 1. So the interesting case, so it's interesting to play the same game now, like that we did for the Ising model for this particular case, because also there you have the exact picture. So again, you can say, okay, so this delta is basically the only parameter that I have in my system. So this will kind of define the hyperplanes on this thing. So when delta is equal to 1 and I only have 2 spins, then the ground state of this Hamiltonian is obviously the singlet. Okay, so really the spin up, down, minus down, up. Okay, this is the Heisenberg Hamiltonian, it's a singlet. And this singlet corresponds to exactly this point. So what I'm plotting here is basically the expectation value of xx and yy. They have to be the same because of the symmetry, and the expectation value of cz. Okay, and then somehow this delta would control the angle between this. So when I have only 2 qubits, this is my reduced density matrix. I have a singlet. Now I ask, okay, let me kind of see what can the ground state be when I have, instead of 2 qubits, I have a whole chain. Okay, so I have my kind of spins. And I want to basically have a singlet here, and here, and here, because this would obviously be the ground state of my full quantum many-body system. I know that locally my energy is minimized if this is a singlet, but of course I also have a term here. This wants to be a singlet, this wants to be a singlet, and that's a frustrated system. I cannot have a singlet here and here at the same time because of the monogamy of entanglement. Okay, there's some constraints there that don't allow me to do this. So what this blue curve is, so just for 2 qubits, this triangle is the full story. All the possible reduced density matrices are just all possible states that lie within this triangle. When I add this full 1 dimensions, then I get this droplet picture. So I start here, and then I get this blue curve, and I start here again. So it turns out that indeed these are the possible reduced density matrices of all possible states in 1 dimension. So how do you get actually this curve? You get this curve by solving some Bethe-Ansatz calculations. Then you go to 2D, and you ask, how does that convex set change as a function of the dimension? Okay, so I go to, instead of a 1D system, a 2D system. Now you have to you can only do this anymore using numerics. What you get is again this diamond, or this curve here, but then you get these red dots. I'm not so sure it's very clear, but there's red dots here. So what you get is this convex set, which is clearly inside the previous one. An interesting feature is already that there's a kind of a full flat piece here. This is completely flat. So that means that indeed in the Heisenberg model in 2D, when you kind of vary this delta, there will be a first order phase transition. Okay, for the same reason as we said before. Now you go to infinite dimensions, and then again the situation becomes very simple. We know that the possible reduced density matrices have to be separable, and for this particular case it's very easy to characterize all separable states. It's exactly the ones that live in this diamond. Okay, so you see that indeed 0 dimension is the big triangle, then 1 dimension is the blue thing, 2 dimensions is this, 3 dimensions would be somewhere here, infinite dimensions is here. So this makes it very clear, and the entanglement basically, so everything here is separable, everything here is very entangled. Okay, so you can even kind of come up with some entanglement measure if you want to kind of the distance from your set of separable states would basically tell you how important, how relevant are quantum correlations for your many-body state. And here you see that there's still lots of entanglement for the Heisenberg model. This would exactly be at the Heisenberg point, you would be here. 2D there's still less, in 3D this will be even less. And yes?
Just 0, 1 and infinite dimensional are analytic, and 2D is inorganic.
Yes, yes, and yeah, indeed. Okay, so I think I have to stop here. It's 10:30, so thanks a lot. So let me just say that from this on we will build now. So we'll try to come up with some intuition and try to build up wave functions that indeed have these extremal properties. How do we build now systematically wave functions that would correspond to the extreme points of this convex set? And this will automatically lead us to the whole field of tensor networks, and then we'll see how to proceed. Yeah, anyway, thanks. Are there questions? You can always come to me during the break.